Hello and welcome. So in this session, we are starting with introduction to Spark SQL, and with it comes introduction to data frames and datasets. Both data frames and datasets are high-level APIs of Spark, whereas RDDs were the low-level APIs. So data frames and datasets are a layer on top of Spark core. Now, because most of the data analysis problems can be described in terms of a SQL command, this layer makes the life of Spark developers really easy to solve these problems. So in today's session, we'll learn about Spark SQL, data frames, data sets. We'll also see how they are different from RDDs. We'll understand what is query optimization that comes as bundled with these APIs, and we'll see what type safety is. All right, so let's dive deeper. What's a data frame? So a data frame is a distributed collection of data organized into named columns. So basically, if you see, RDD was collection of unstructured data. Every record in an RDD could be just simple row in your text file, right? And to perform any operation on RDD, you would first manipulate that data using, let's say, split, convert it into key values, and then apply some operations, right? So whatever structure you are providing to data, you are providing it yourself. Whereas in case of data frames, they are structured from the get-go. So data frames provide a higher level abstraction compared to the RDDs. A data frame can be thought of as a table in a relational database, or a data frame in Python's pandas library, right? The data frame in Spark offers a structured and the schema-based approach to working with data. It provides rich optimizations and built-in functions for data manipulation, filtering, aggregation, and more. Data frames can be created from various data sources, including structured data files like CSV, JSON, Parquet, etc. It can, interact with other JDBC, ODBC like technologies, database technologies, and it can obviously interact with the existing RDDs. You can convert your existing RDDs into data frames and so on. Right. So what are the main features of data frames? So as we discussed, the first main feature, the biggest feature of data frames is they have a schema. So they have a well-defined schema which specifies the column names and their corresponding data types as well. The schema helps ensure data consistency and enables Spark to perform advanced optimization during query execution. They are immutable and distributed. So just like RDDs, data frames are immutable and distributed in nature. They are divided into partitions and processed in parallel across the cluster of machines. So that provides a lot of scalability and fault tolerance. Just like RDDs, they also have lazy evaluation, which means the operations on data frames are not executed immediately. Instead, Spark optimizes and combines transformations into an execution plan, which is then executed when an action is triggered. Right? One of the most important features of data frames is their catalyst optimizer. So Spark's catalyst optimizer is responsible for optimizing data frame operations. So it basically, figures out which predicates can be pushed down to source data itself. It can reorder your joins, filter operations. So basically, it applies all the query optimization techniques that are available in the world of relational databases, right? And then obviously, because it's data frames are like relational database tables, you can run SQL queries on top of them, and data frames are integrated with the whole Spark ecosystem. They seamlessly integrate with the Spark components such as Spark SQL, Spark Streaming, Machine Learning Library, GraphX. So this enables unified data processing across different Spark modules. All right. So let's try to understand how exactly data frames optimized execution plan works. Let's think of this example where you are trying to join two data frames together, students and classes. Both of them contain an ID. Students data frame contains student ID, SID, and classes data frame contains class ID, CID. Okay, you are trying to join them, and then you are trying to filter on only those classes that started, let's say, after a particular date. Now, in this case, a logical query plan would be to scan the student's data frame, basically data source, and then scan the classes data source, join them together based on the ID, and then apply the filter. Right? So that's like the logical flow of steps, just the way you have described in the query. Let's say if there is no optimization happening, this is the query plan that would be executed, right? But we all know that because there is a filter clause in this operation, right? And if, just think about it in your head, if let's say we could filter the data before joining, then your classes data set would have already reduced even before the join happens, right? And because join is an expensive operation, it makes sense to apply filter before join, right? So we can optimize it like in our head. So that's what Spark DataFrames do. They come up with an optimized plan where you scan the classes data frame and you apply the filter before the join. Now your classes data frame is reduced in size, and then you apply the join operation with the student's data frame, so that the join operation, which is an expensive operation, has to work on lesser amount of data. Make sense? There is actually one more optimization that Spark DataFrames can use wherever possible, and that is, when your data sources themselves are intelligent. Now think about a data source which itself can, apply that filter. Think of an external database, okay, a relational database. So instead of scanning the whole classes data set into bringing it into memory and then applying the filter, isn't it better that you send a query to that data source itself that give me only those classes records where, let's say, date is greater than this. So which means you are pushing the predicate down to the data source itself. In that case, you are not even bringing that data into memory. You are bringing only the filtered data into memory, and then you are applying the join. So it is even more optimized than the second option, right? So this is how data frames really optimize your query plans, and that is why they are much better than RDDs, because in case of RDDs you don't have any such optimization available. Make sense? Hope so. All right. While data frames in Spark offer numerous advantages, there are also a few drawbacks to consider. I'm sure you should be aware of the drawbacks as well when you start using them. So first and biggest drawback that data frames have is lack of type safety. Although data frames provide a schema-based approach, the type safety is not as strong as in statically typed languages. So errors related to column names or types might only be caught at runtime rather than during compilation, because data frames, they infer their schema at runtime only. So if, let's say, some data which you have loaded into a data frame does not contain a particular column, and you still try to run a query on that column name which does not exist in that data frame, it will not let you know about that problem at the compile time. You will only come to know about this problem at the runtime. So at runtime, you will get an exception which will say that this column does not exist, which means it's an expensive mistake, right? Because any problem that you could have caught at compile time, but you're not catching it at compile time, but catching it at runtime, it's definitely an expensive mistake. There is some serialization overhead that data frames have. They rely on serialization and deserialization of data, which introduces some overhead in terms of CPU usage and network bandwidth. This can be especially noticeable when working with complex data types or when performing extensive data shuffling, right? Then data frames provide very limited flexibility because they are designed for structured data, right, and impose certain restrictions on data manipulation. Complex nested data structures or unstructured data may not fit well into data frames model. So in that case, obviously you have the RDD API available, and you can actually manipulate data with RDDs a little bit, and once you have converted that data into structured data, then you can convert those RDDs into data frames and take all the advantages of data frames. Make sense? But despite these drawbacks, right, data frames remain a powerful and widely used abstraction in Spark due to their ease of use. They have optimized execution and integration with the Spark ecosystem. So understanding these limitations and their potential impact can help developers make informed decisions when working with data frames and determine whether they are the right choice for their specific use case or not. Right. So let's come to datasets. So datasets uh, is actually an abstraction on top of data frames as well, right? Whatever drawbacks that we kind of saw in as part of data frames, some of those drawbacks have been solved in datasets. And one of those drawbacks that has been solved in datasets is strong typing. So we saw that there is a lack of type safety in data frames. Datasets actually solve that problem. So datasets introduce a strongly typed API, allowing Spark to perform compile time type checking. So this helps catch errors early during development and provides better integration with IDEs and tools that support type-aware, auto completion and refactoring kind of stuff. Then datasets are, they support object-oriented programming. They are based on object-oriented programming concepts, allowing developers to use classes or Java beans to define the structure of the data. This enables easy integration with the existing code bases and enhances code readability and maintainability as well. So basically, in case of datasets, you can define a case class where you define the structure or schema of the data, and then you use that case class to create a dataset from a data frame. That's it, right? It's integrated with the DataFrame API. It actually extends the DataFrame API, meaning it can leverage all the advantages of the DataFrame API, all the optimizations that DataFrame API provides, and it actually is better than DataFrame's API in that sense, right? One problem with datasets is that because it is kind of statically typed, it cannot be made available in Python because Python is not a compiled language. So as of now, at least, datasets are available only in Scala and Java, and they are not available in Python. So overall, Spark datasets bridge the gap between RDDs and data frames by providing a strongly typed object-oriented API that benefits from Spark's optimizations and query processing capabilities. They offer improved type safety, better performance, and seamless integration with Spark's structured data processing ecosystem. So that's it about the introduction. In the next sessions, we'll dive deeper into datasets and data frames, and we'll start with some hands-on exercises. These are actually, one of the most important concepts of Spark ecosystem. So stay tuned. See you later. Thank you.